Well, welcome everyone. Great pleasure to introduce the invited speaker for HM this year. So to inform Allison, we have one speaker that we invite typically for the department, and you won the Popular Choice Award because both faculty and students suggested your name independently, and there's crosscuts across different themes, and so that was easy. So Allison grew up outside of New York City, went to Cornell for her BS, and got interested in doing hurricanes. So reached out to Carrie Emanuel, and did her PhD there, and very sensibly thought that she would do something related to rotation on hurricanes, but turned out her PhD thesis has no, it's in a non-rotating framework. Since then has moved to FSU since like 2017, professor there, endowed even, and this is the title of your talk, so welcome.
Thank you very much, Vikita, for the introduction and for the invitation to come visit here. It's really exciting. I've never been to Miami before, not to the school here, nor the city of Miami. So I'm looking forward to seeing more of it. So today I'm going to talk about some, sorry, I need my mouse on this screen. Okay, so today I'm going to talk about some recent work in my research group on the acceleration of tropical cyclone development by cloud-radiative feedbacks. And I don't think much broad motivation is necessary for this particular audience, but very briefly, we had this notable major hurricane drought in the US for 12 years after Hurricane Wilma. And then what changed finally to end the drought was that I moved to Florida. So I moved to Florida in 2017, and after that, the Gulf Coast has basically been hammered by 7 major hurricanes making landfall in the last six years, all of which underwent rapid intensification. So Harvey, Irma, Michael, which was terrifyingly close to Tallahassee, Laura, Ida, Ian, and then Idalia just this past fall, which was also terrifyingly close to Tallahassee. And given these recent high-impact hurricane events, it really heightens the importance of our ability to forecast them effectively, as well as understand the processes underlying tropical cyclone development. And the good news is that after many years of not having much progress in intensity forecast errors, finally in the last decade or so, we've seen really impressive improvements in forecasting. So these are the National Hurricane Center's intensity error as a function of lead time. But despite that progress, challenges still remain, especially regarding forecasting rapid intensification. And so this is an example showing the probability of detecting rapid intensification in both black, the official forecast, and then the red or blue are one statistical and one dynamical model. So it has gone up, but these probabilities are still quite low. So that's sort of general motivation for continuing to improve those abilities. On the genesis side of things, global forecast models have also become a more reliable source of tropical cyclone genesis guidance in recent years. And then beyond forecasting, climate models have also improved such that they can reproduce the basic pattern of tropical cyclone activity with some fidelity and exhibit some skill in seasonal forecasting. So this is an example of one climate model showing the hurricane tracks. This is like 30 years of hurricane tracks over historical simulation compared to observed hurricane tracks over the same period. And if you look at them, you're like, okay, that looks pretty good. They're more or less putting the hurricanes in the right places, getting roughly the right number. And this is really important because we do not currently have a physical theory for what controls global tropical cyclone frequency. And so our projections of future TC activity rely heavily on global models, and thus trusting their ability to accurately simulate the TC climatology is important. Now, I picked out a good example here. If we look at a broader range of climate models, we can see clearly that there are still problems. So these are a variety of different models. Many of them are CMIP5 models. There's also some higher resolution climate models thrown in there. So various things about different on all these. And you can see that there's a huge diversity in terms of their ability to represent the spatial distribution of TC tracks. Some of them look pretty good, some of them have hardly any storms at all. And these biases hold for intensity as well. And so even high resolution climate models, and by high resolution climate models, we're talking usually about 1/4 degree, 25 kilometers here, even those struggle to reproduce the observed distribution of TC intensity. So the colored lines here are a whole bunch of different high resolution climate models. The black line is the observed PDF of intensity from IV tracks. And you can see that none of them really get category 3 storms. And so we know that resolution is a big part of this, but even at the same resolution, there can be a broad spread across climate models in their ability to represent TCs. And so this is showing ACE, accumulated cyclone energy, over the entire tropics as a sort of bulk metric of tropical cyclone activity as a function of the model resolution. And so yes, the models at higher resolutions are able to produce more tropical cyclone activity. But if you, for example, look at this collection of models at 1/2 degree or this at 1/4 degree, you can see that there's still a lot of differences even at the same resolution. And in a subsequent paper, we examined this and noted that the reasons for the differences in these models at a given resolution is not due to the large-scale environment. It's not like one model is producing, way more wind shear or something than the others on average. It's due to something else. And so all of this sort of motivates gaining a better understanding of the physical processes controlling tropical cyclone development, both so that we can continue to improve our ability to forecast them, as well as continue to improve our ability to represent tropical cyclones in climate models. And there's many different physical processes that are important for TC development. I'm going to focus in this talk on just one particular one, cloud-radiative feedbacks. And so why am I talking about this? Where did we come from in terms of thinking about radiation being important for tropical cyclones? Well, at least for me, I became interested in it because of growing evidence for the importance of radiation for TCs along two fairly independent sort of bodies of work. One is the realization that tropical cyclones have a diurnal cycle. So here's an example from Jason Dunyon's well-known paper showing these outward propagating cold diurnal pulses in the convection tied to the diurnal cycle. Subsequent studies have linked this also to diurnal variability in other elements of the tropical cyclone structure. And so this body of work makes very clear that variability in radiation affects tropical cyclones. And then in a whole other line of work, studying convective organization more generally, including my PhD work studying non-rotating convective aggregation, we've learned that cloud-radiative feedbacks are really essential for helping clouds and convection cluster together, as shown in an example here in this global cloud resolving model simulation. So convection can spontaneously organize due to these radiative feedbacks. And so it seems plausible then that these radiative feedbacks could also contribute to tropical cyclone or influence tropical cyclone development. Why would that be, or why do we even have cloud-radiative feedbacks in the first place? So this is not a tropical cyclone. This is a mesoscale convective system over the tropical Eastern Pacific, a picture I took during the OTRAC field campaign. I love any excuse to use this picture because I think it looks just like a textbook image of an MCS. It's really amazing, overshooting tops and everything. And so essentially, deep clouds with lots of water droplets and ice crystals create a localized greenhouse effect that trap heat and warm the atmosphere there, and then we have strong radiative cooling at the top of those clouds. And so since the radiative heating rate in the atmosphere depends on clouds and water vapor, which of course vary spatially in a developing storm, this drives spatiotemporal variability in the radiative heating and cooling rates, which then can drive circulations and have the potential for feedbacks on the development of that storm system. And so this sort of realization and investigation of the role that radiation in general and cloud-radiative feedbacks more specifically might play in various aspects of tropical cyclones, including their structure, their intensity, their formation, it has been the subject of a rapidly growing sort of body of work, including some work done by students and faculty here, and much of this work has been done doing models, but there's been some observational work as well. So given that backdrop, what have we been working on with regards to this problem? Our approach is twofold. One is to perform idealized cloud resolving model simulations with the SAM model, and the other is to utilize satellite observations of clouds and perform radiative transfer calculations, which is work led by my PhD student, Sun Young Lee. And so I'm going to first talk about the cloud resolving simulations, and then I will talk about the satellite observations at the end. So the types of simulations that we use are shown here in a schematic. They're idealized in that we're not trying to represent one specific storm, but just a generic tropical cyclone initialized from an idealized state. And so we initialize these simulations from a mesoscale warm saturated bubble that's on an F-plane in an otherwise quiescent and moist neutral environment. And we do so on a domain that's about 2,000 by 2,000 kilometers in each horizontal dimension with 2 kilometer grid spacing and then 74 vertical levels, doubly periodic boundary conditions. And this was results in a paper that I wrote a couple of years ago. Now, the nice thing about working with models is that you can perform mechanism denial experiments where you remove or alter certain physical processes and see what the influence of that is on whatever phenomena you're investigating. So that's what we do with these simulations here. We can compare, at least initially in this slide, a control simulation in which we have the fully interactive radiation. So the radiative heating and cooling rates are calculated by the radiative transfer model, at every radiation time step according to the simulated clouds and water vapor, and so on and so forth. And that'll be the simulation on the left. And then we'll compare that to one in which we removed radiative feedbacks by horizontally homogenizing the radiative heating rate at every level, at every time step. So we're still calculating the radiative heating rate, but we're homogenizing it spatially before it's being applied as a tendency. So effectively, the dynamics in the model feel the same radiation everywhere. So what we're looking at here is hourly average wind speed at the lowest model level. So after a sort of initial rapid adjustment to that moist bubble to get sort of weak vortex in balance with that moisture and temperature perturbation. In this control simulation on the left with radiative feedbacks, that rapidly spins up into a tropical cyclone. Here, the color bar is capped, it goes higher than 50 meters per second. Whereas in the simulation on the right, it took a lot longer for things to get going. So I'm going to play it again. So there's that initial development. Here we now have this weak vortex. Already by just a few days, 3 days or so into the simulation, we have tropical storm force winds, whereas the one without radiative feedbacks, we still just have this weak vortex that hasn't intensified, it hasn't contracted. Now it does do so eventually, so radiative feedbacks are not necessary for tropical cyclone development in these simulations, but they certainly help. It takes about half the amount of time to form the tropical cyclone when you have radiative feedbacks than when you don't. And this you can see more quantitatively if you look at the time evolution of the maximum wind speed in the simulations, in the control simulation in black, and then these homogenized radiation simulations in gray. And we do a small 5-member ensemble for each set of experiments by adding some small amplitude white noise on top of that bubble perturbation. And so with radiative feedbacks, we see that convection, which we're sort of looking at by examining outgoing and long-wave radiation, is an indicator of where deep convection is. Convection quickly organizes in association with moistening. So the yellow to blue shading here shows precipitable water. So with radiative feedbacks, we have that convective deepening, organization, and moistening of the sort of center of the storm with drying the periphery. On the other hand, in the panel on the right here, in the simulation without radiative feedbacks, Convection remains disorganized, shallow, and weak, and that moistening is much, much more slow to occur, sort of damped, without having the spatial variability and radiative feedbacks to amplify the moistening and drying anomalies. So this again suggests that radiative feedbacks have an effect, but what we're interested in is, well, which part of the radiative feedback is it? Because we know that radiation, obviously there's both shortwave and longwave, and they're influenced both by variability in water vapor as well as ice clouds and liquid clouds. So we want to try to isolate which is the one that's contributing most to this acceleration of TC development. So in order to do that, we've done additional sets of simulations. This is just another way of removing the radiative feedbacks. Instead of spatially homogenizing the radiative heating, in this case, we're actually prescribing it to a uniform vertical profile driven from the mean of a prior simulation. That's also effective at slowing down the TC development and removing those radiative feedbacks. But we can then do this separately for shortwave and longwave. So these are the profiles that are prescribed. So for example, we can prescribe the shortwave heating rate and let the longwave still be calculated interactively. And if we do that, we get this set of simulations here, which lies pretty much on top of the control ensemble. Maybe the hurricane forms even a little bit more quickly. And so this suggests that the shortwave radiative feedback is not the key thing accelerating TC development here, because when we don't have it, things proceed more or less as normal. We can do the same thing, prescribe just the long wave, so remove the long wave feedback, but still have the shortwave feedback, and we get this blue set of lines, which very much delays the tropical cyclone development, perhaps even more so than if you remove both long wave and short wave together. So this indicates that it's really the long wave feedback that is contributing to accelerating the TC development, and when we don't have it, TC development is much more slow to occur. Okay, so it's long wave. What about water vapor versus clouds? Which is more important for driving the spatial variability that gives rise to this feedback? So the next set of experiments we do is where we specify the water vapor profile in the radiation calculation. So this is done only in what the radiation calculation sees. The rest of the model still sees the moisture content that has been, predicted. So it's just the radiation is seeing the same water vapor profile everywhere. And if we do that, regardless of whether we do that for shortwave or for longwave or for both together, those curves are in these colored dashed lines, which are pretty much all on top of each other. So removing the spatial variability of water vapor in terms of radiation does not have a big influence on the tropical cyclone development. So probably not the key factor. That leaves clouds, and we can examine clouds by separately considering liquid clouds and ice clouds, by zeroing out the cloud amount that's seen, or the cloud condensate path that's seen by the radiation scheme, or you can think of it of making the clouds transparent to radiation. So if we do that for the liquid clouds, make them invisible, we get this set of green lines, not so different than the control. If we remove the ice clouds, the cyan lines here, that gives us a slight delay in tropical cyclone development and then a reduction in the intensification rate after we have a sort of tropical storm form. So this suggests that ice clouds play a much bigger role than liquid clouds do. And then if we zero out both the ice and liquid clouds together, we get these gray curves here, which is an even bigger delay. So there definitely is some sort of nonlinear interaction between the ice and liquid clouds. And zeroing out the clouds is almost as effective at removing the radiative feedbacks as prescribing the radiative heating rate completely. So these set of experiments suggest the acceleration of TC development by radiative feedback is most prominently contributed by the radiative effects of ice clouds on the long wave. We can look at this in more detail by examining the radial anomalies of the long wave radiative heating rate. So that's what's plotted in the color shading here. Red colors mean that we have heating relative to the radial mean. Blue colors means there's anomalous cooling. Doesn't mean it's actually heating, but just anomalously. And then there's a whole bunch of other contours on here. The cyan contours are a couple different values of the ice water condensate amount, and then the green contours are liquid condensate. The black line shows the radius of maximum wind as well, and then we have time going down from day 1 through day 5 of the simulation. So in the control simulation with the fully varying radiative heating, we see that we have, as the storm starts to develop, we have local low to mid tropospheric warming underneath the sort of ice cloud tops in this red color shading here. And relative to the surrounding areas, that of course amplifies as the storm starts to develop. You also have cooling at those cloud tops shown in the blue colors here. This spatial variability in the radiative heating rates strengthens the transverse circulation. So what's shown here are radial and vertical winds. So the color shading is the radial wind, where blue is inward towards the center of the storm, which is at the left side, and then red is outwards, and then the contours show vertical motion. So this spatial variability in radiative heating, long-wave radiative heating, generates a deep in, up, out circulation. Whereas if we zero the clouds felt seen by radiation, we get the second panel for each of these figures. The first one, you can't really see anything, especially on the projector, and this emphasizes that making the clouds transparent is very effective at removing most of the spatial variability in radiative heating, and consequently, the circulation is much slower to develop. You don't really have low-level inflow of any substantial magnitude until after day 5 in the simulations, where that starts to develop already by day 3 when you do have the spatial variability of the cloud-radiative effects. So this local warming from the effects of these ice clouds strengthens this transverse overturning circulation, enhancing ascent in the inner core of the developing tropical cyclone. And this also contributes to moistening in the atmosphere. So this final panel shows relative humidity, again in our control and zero cloud simulations. And so we can see that in our control simulation, we saturate our column in the inner core within the first couple of days, whereas in the zero cloud simulation, we still have sort of low relative humidities in the mid layers all the way through day 5. You also have less of a gradient in that relative humidity, so with the moistening in the inner core also comes the drying in the outer regions in the control simulation. So these results again sort of suggested the mechanism for how cloud-radiative feedbacks affect tropical cyclones, but we'd like to be a little bit more quantitative about measuring the strength of that long-wave cloud feedback. And so in order to do so, I'm going to utilize the budget for the column integrated frozen by static energy variance budget. Just a bit of a mouthful. We developed this during my PhD to apply to convective organization, and subsequently adapted it to using TCs and cloud resolving models and GCMs, and other people have used it in other contexts as well since then. And the main thing I guess to take away from this is that each of these colored boxes is highlighting one of these so-called feedback terms, which consists of a product between the anomaly in the column integrated moist static energy, this H hat prime, and something that's a source or sink of moist static energy. So those sources and sinks are our surface enthalpy fluxes, our column shortwave flux convergence, our column longwave flux convergence, and infection. And so if you have a situation where you have a process that is acting to increase the moist static energy of an already moist high MSE region, that contributes to enhancing those MSE anomalies, increasing that spatial variance, and contributing to the moist dry region and TC formation. Effectively, this is measuring how different processes contribute to making moist regions moister and dry regions drier. And this is at least empirically related to TC intensity in these and other simulations. So this shows the spatial variance of the column MSE plotted against the maximum intensity in our whole suite of different simulations, only up until the time of the lifetime maximum intensity. So it indicates that this MSE variance is a really effective measure for the sort of local warming and moistening that characterizes TC development. And this is consistent, again, with other sort of work as well. So given that the MSE variance increases as the TC intensifies, so the moist regions get moister, the dry regions get drier, we can then use this MSE variance budget to say, okay, what are the magnitudes of all the different physical processes contributing in the budget to that increase in MSE variance? And so that's what's shown here. The green, focus just on the solid lines, I ignore the dashed lines for now. The green line here is our surface flux feedback. And so the surface fluxes are typically larger where you have your stronger winds close to the center of the developing storm, and once there is one, the eye wall, which is the same place where we have higher moist static energy, more moist conditions. So that's a positive feedback. The blue line here is our long wave radiated feedback, again based on the spatial variability in that column, long wave cooling, so how much the atmosphere itself is cooling or heating due to radiation. The red one is the shortwave feedback, and then the pink line here is the advective feedback. And then you can't see it too well, but there is, this gray line is the residual in the budget. So I actually calculate all the terms in this budget online in the model as it's running, and it closes pretty well. So focusing on the green and the blue lines, because those are the largest positive feedbacks. Oh, sorry, the black line is the total tendency. So the green and the blue are the largest positive feedbacks contributing to this sort of moist static energy anomaly amplification. The long wave feedback is contributing the most relative to the surface feedback in the early stages. So the sort of ratio between them is highest in the early stages of TC development, which is this kind of 2 to 4 day period that I've highlighted here. But even as we get later in the simulation, so the max intensity for this control simulation is reached around days 6 to 7, even at that time, the long wave feedback still matters. It still is about a third of the magnitude of the surface flux feedback. So yes, the surface flux feedback, which is really capturing Wishy, is the most dominant process as we're kind of getting that rapid intensification up to the max intensity. But the long wave feedback is not negligible. It's still helping things along even at that process, and it's especially important in the early stages. So we can then look at just that long wave feedback itself in all of our different simulations where we messed around to remove various different aspects of the radiated feedback. And again, the magnitude of this number is telling us how effective is the spatial variability in long wave heating. How effective is that at enhancing the moist static energy or moisture mostly anomalies and thus aiding the TC development? So this again is now only the long wave feedback. All the different lines are our different simulations. And the main thing to point out is that our simulations in which we have made the ice clouds transparent, either on their own or in concert with other aspects of the radiation, those are all those lines that are collected around 0. So there's basically 0 long wave feedback in these simulations with transparent ice clouds, again emphasizing that removing the radiative effects of ice clouds is very effective at removing the spatial variability in radiative heating and cooling. However, I do also want to point out that in this blue dashed line, that's the simulation in which we prescribed the water vapor in the long wave calculation. And our long wave feedback is a little bit weaker in that simulation compared to the black in the control. So even though it didn't seem to have that big of an influence on the ultimate tropical cyclone development, the spatial variability in water vapor does contribute at least a little bit to our long wave feedback here. Okay, so this is nice, but one challenge in comparing our different simulations in this context is that they all form tropical cyclones eventually, but they do so at different times. And so, at day 3 in the control, we have a tropical storm, whereas in the other simulations we have nothing. So we can also compare the magnitudes of these feedbacks composited over just time steps in which the tropical cyclones have, across the different simulations, have the same intensity. So this is showing that long wave feedback in each of our simulations, just average over the times prior to the max intensity, in which the intensity is between 12 and 15 meters per second. So this is kind of just before it's starting to reach that tropical storm strength intensity. And what you'll notice is there's kind of really 2 clusters of simulations. These, which are ones in which We reach tropical storm strength in about 3 days, and then this set where it takes much longer than that. And the difference between these two is that these sort of gray and various types of gray and blue points here are all the simulations that don't have cloud-radiative feedbacks at all. And they take much longer for the initial development of the tropical cyclone and for it to reach tropical storm strength. And so it's kind of somewhat of a binary. You either have the cloud-radiative feedbacks or you don't, and the existence of them allows you to proceed much more quickly. But then the second question is like, okay, well, what about after the tropical storm forms? Do the differences in the strength of the long wave feedbacks, still play a role? Because we can see here that across this group of simulations, there's still, almost a factor of 3 difference in the actual magnitude of the long wave feedback. So this is showing that same long wave feedback at that sort of just before tropical storm force intensity, but now it's plotted against the average intensification rate between reaching tropical storm force and the lifetime maximum intensity, which these all reach max intensities equivalent to like Cat 4 or Cat 5 strength, shown in meters per second per day. So we see a relationship here in which simulations which at the same intensity at that moment have stronger long wave feedbacks, they have faster intensification rates. Now you might say, well, is that correlation, which is high, it's 0.82. I actually forget the difference between these two correlation orders. Is that driven by just having these kind of 2 clusters of models, the ones that basically have 0 long wave feedback and the ones that don't? It's not. I think actually what's that these numbers? I think that 0.98 is if it's all the simulations, and 0.82 is, I believe, if you take only this set of simulations. So if you kind of restrict your correlation just to the set of simulations that has the long wave feedback in the first place, we still see a relationship there based on the magnitude of that feedback, such that those that have stronger feedbacks have faster intensification rates. And so this is really suggesting that the existence of cloud-radiative feedbacks contributes to the initial sort of genesis or development of the tropical cyclone, helping that proceed a little bit more quickly, or in these simulations a lot more quickly than if you didn't have it. But then even once the tropical storm has formed, then variability in the strength of these long wave feedbacks can contribute to how quickly it's able to intensify. Okay, so that wraps up the modeling part of this presentation. And so the remaining 10 to 15 minutes, I want to talk about looking at similar processes in observations, because this is all very nice, but it's in a model, it's very idealized, right? Tropical cyclone spinning up from a bubble. It's a very favorable environment for the tropical cyclone to form. What about in the real world? So in order to do that, we're going to use satellite data. And so prior work that has used series and CloudSat measurements, this is Shannon Wu's work, found that intensifying tropical cyclones, these ones here, have greater radiative heating from clouds in the tropical cyclone area compared to weakening ones, and thus have stronger cloud-radiative feedbacks. And so this is really nice evidence from satellite data that we're seeing some of the same sorts of relationships that we've seen in models. Intensifying storms compared to weakening storms have stronger cloud-radiative feedbacks. What our goals are to do is to build on that work to investigate not just the radial, but also the vertical structure of the radiative heating in real tropical cyclones, and then decompose that into contributions from ice clouds, liquid clouds, and water vapor, and then diagnose the radiatively driven circulation that develops and assess its role in TC development. And so this is work of my PhD student, Sun-Young Lee. And so to do this, we're using the CloudSat tropical cyclone database, which collects CloudSat overpasses within 1,000 kilometers of the TC center from 2006 to 2019. So CloudSat carries a cloud profiling radar, which is a W-band instrument, so it's sensitive to cloud droplets. This is an example of, I think, Typhoon Fanapi, I believe. Yes, Fanapi in 2010 in the Pacific, showing an example of what that looks like. So, each CloudSat overpass is basically just one line that maybe intersects with a tropical cyclone, but it has, very high resolution in the vertical, to show the detailed sort of picture of this vertical structure. So sometimes you get lucky and you have an overpass right through the center of the storm, but most of the time you don't, right? Sometimes you don't hit a storm at all, or it's maybe catching just aside. And so any single storm is very poorly sampled by CloudSat. And so in order to understand the spatial structure of the clouds and consequently the radiative heating, we need to composite over many, many overpasses. And the way that we construct our composites is based on the intensification rate. And so we consider the 24-hour intensification rate from Ivy tracks centered around the time of the CloudSat overpass. And we only include overpasses that occur for a given storm prior to its lifetime maximum intensity to really focus on the sort of initial stage of development, as well as we limit ourselves to storms basically weaker than category 2, so intensities less than 42 meters per second. And this is based on evidence from prior work that suggested the radiative feedbacks really play the biggest role in weaker tropical cyclones, again at the early stages of development. And then we split this up into bins based on the intensification rate from neutral, slow, fast, and rapidly intensifying storms. So these are the 24-hour intensification rates. Now, I will note that in these intensification rate bins, there are samples of different intensities themselves. So it is possible that there's contributions from TC intensity as well in distinguishing our composites. But at least for this particular sample of storms that we're considering, where we're limiting it, just through, category 1 storms and this particular CloudSat overpass data set, it turns out that the average intensity in each of our intensification rate bins is near 20 meters per second in all of them. So we think that, as I'll show, there are differences based on the intensification rate, and we think that these really are reflecting differences based on intensification rate, not driven by intensity itself. Ideally, you composite over both things, but there's just not enough data to do that. Okay, so this shows what things look like once you do those composites. The color shading here is showing specific humidity, which are from East and WF analyses, which have been co-located to the CloudSat data. And then the contours here are showing a couple contours of ice water content. So obviously we have most of our ice clouds, limited, ice water content within 300 or 400 kilometers of TC center, so this is height and radius. And then you can compare this to the different intensification rates. So these are now showing the difference between rapidly intensifying storms and the other categories. And so we find, as has been also shown by prior work, that the greater intensification rates has greater water vapor and greater ice content, especially within 200 to 300 kilometers of the TC center. Okay. So this is just kind of sanity check. We're analyzing the data the right way. The question then is, okay, what is the implication of that for the radiation, right? The different amounts of water vapor, the different amounts of ice should affect the radiative heating rates. So in order to assess that, we take the CloudSat retrievals of cloud properties, as well as some data from the East and WF analyses, and run it through RRTMG to calculate radiative heating rates. There are radiative heating rates provided by the CloudSat product, but they don't separate them out by the contribution from different hydrometeors, so that's why we did our own calculations so that we can later on look at the decompositions of things. So this is showing the results of that calculation. Again, so the ice is from the CloudSat 2C ICE product, which actually combines CloudSat retrievals as well as Calypso retrievals of ice, which helps it be better representing thin ice. Liquid from the CloudSat only, and then the water vapor and temperature and ozone and things like that go into it are from the East and WF product. So the left here shows the long wave heating rate, the right is the short wave during daytime only, again as an anomaly from the mean across all radii. And so it looks very similar to what I showed for the model data. You have this anomalous long wave warming in the lower troposphere and mid-upper troposphere close to the TC center, where we have all of this ice, and long wave cooling at the convective cloud tops. For the short wave, we have short wave heating at the cloud tops and cooling below. How does this differ in our storms of different intensification rates? So basically for the long wave, if you see brown in the same place there was red in the RI1, that means that there is less heating. So this says that our rapidly intensifying cases have greater long-wave warming in the inner core. So basically, these browns that you're seeing here indicate less warming in slow intensifying and neutral storms compared to the rapidly intensifying. And then for shortwave, the signs sort of reverse. So where we see the purple, that means there's less cooling. So the slow and neutral intensifying cases have less shortwave cooling in the inner core than the rapidly intensifying ones, and they have less shortwave heating at cloud top. And so it pretty much follows, how much cloud amount you have. If you have more ice, more water vapor, more liquid, you're going to have larger radiative heating rate anomalies in that region. And we can distinguish between the contributions of these different factors that affect radiation by rerunning the radiative calculation, in which we zero out the liquid clouds, zero out the ice clouds, use just clear sky sort of processes where we zero all the clouds in order to decompose which is contributing most to the spatial variability. We also are interested in the circulation effect mediated or driven by the spatial variability in heating. And so in order to assess that, we calculate the balanced circulation response to that radiative heating using the Sawyer-Lassen equation. And so what's shown in this plot here, so this is for the rapidly intensifying cases only, though we have done this also for all the other ones. What's plotted here is the longwave heating rate anomaly, so this color shading is the same as on the previous figure. And then the contours show the stream function calculated from the Sawyer-Lassen equation, driven by these longwave radiative heating rates. And then the little vector arrows, which are hard to see, show the actual circulation vectors. So again, this emphasizes that you generate this sort of deep in, up, out circulation. And if you sort of separate that out to whether it's coming from the lower mid-tropospheric warming versus the upper tropospheric cooling, it's mostly the lower mid-tropospheric warming that's driving this. And then we can do this for, again, our different mechanism denial experiments where different things are held fixed or not. So the bottom left here is showing the contribution of clouds alone. The top right is showing the contribution of only ice clouds. And then the bottom is showing the contribution of only liquid clouds. So you can see that if we're looking at only the radiative effects and the subsequent circulation to provide liquid clouds, there's not a whole lot going on. There's a little bit of variability, so you get this sort of shallow returning circulation. If we look at just the affected ice clouds, we capture much of the same sort of total cloud or even total cloud plus water vapor response, though missing some of the lower tropospheric variability, but that's really giving us most of this deep in, up, out circulation, which is contributing to the tropical cyclone development. So just like in the model simulations here, the spatial variability in the radiative heating rates and the subsequent radially driven overturning circulation are dominated by the contribution from ice clouds. But liquid clouds, and actually more so water vapor, are important for driving what's going on in the lower troposphere. So for example, if you compare the top left with the bottom left, you see that when we're considering only clouds, we miss some of this lower troposphere warming, and so water vapor does contribute a bit there as well. So then the final thing is to take this and then actually compute the radiative feedback in terms of the moist static energy variance budget. So same thing as before, looking just at the radiative terms here. We use the temperature and water vapor from the ECMWF analyses to compute the moist static energy here. We compared this to looking at sort of just the moisture in the tropics in general, and even in tropical cyclones, moisture variability contributes more to moist static energy variability than temperature. So you could approximate the column integrated moist static energy with the column water vapor or precipitable water, of which we do have satellite retrievals for that, microwave retrievals from example, the AMSTER-E satellite. The AMSTER-E precipitable water measurements are co-located to the CloudSat data in this data set, but only for 2 years. And so for those 2 years, we did compare using the AMSTER-E PW retrievals to the ECMWF precipitable water, just to make sure that using the model data wasn't going to be totally wrong. And there is a little bit of bias. I think the model underestimates the amount of water of crystalline water, especially in the inner core. But in terms of the spatial variability, which is what matters for this budget calculation, they're nearly identical. So that gave us confidence to use the ECNWF product, which allowed us to use the full length of the data set. And so what's shown here are these radiative feedbacks as a function of radius in the simulations, just in the sort of inner core out to 300 kilometers. And then the plots on the right show the feedbacks averaged over different sort of radial rings. So 0 to 200, and then the full 0 to 1,000 kilometer radius. And then the top is long wave, middle is short wave, and bottom is the net. And then finally, all the different colored lines are our different intensification rate bins, where the red are the rapidly intensifying storms. So first, if you focus on the bottom plot here, this is the net, the total radiative feedback. It's positive, basically. So that suggests that for all the storms here, the radiative feedback is contributing to moistening the TC core and helping TC development. If we separate that out to long wave and short wave, we see that it's much larger in the long wave, because basically the vertical structure of the short wave heating rates is in the sense that it would actually oppose the TC development, but a lot of it cancels out when you do the vertical interval. Focusing on the long wave, we see that the red curves that are rapidly intensifying cases have the greatest long wave feedback in the inner core, which is true if we look at individual radii here, as well as average over the entire inner core. If you average over the whole region, they're not distinguishable from each other. And if you do this separately for all the different versions of the radiative transfer calculation, this is, again, coming from the ice clouds. For the shortwave cases, most of them are near 0 for the shortwave feedback, but the rapidly intensifying cases actually have a negative shortwave feedback. And this is an effect of clouds. And so if you calculate just the clear sky shortwave feedback, that's positive for both the rapidly and fast intensifying cases. It's greatest for the fast intensifying cases. So essentially what's happening is that the rapidly intensifying storms have so much ice water content in their inner core that it's really effective at blocking shortwave radiation from getting in where it can be absorbed by the moisture there. And so that's why it's a negative feedback. You actually have reduced shortwave heating in the inner core because there's so much ice cloud there. And these results are very consistent with model simulations, both my own and from other authors, as well as the prior observational work. Okay, so then the very last thing before I conclude, and this is still ongoing work, is to say, okay, we have now this good estimate from satellite data of what these radiative feedbacks are, composited of intensification rate. We've also separately composited it by intensity. But let's connect this back to the motivation in the beginning about, how can we improve how climate models represent TCs? Are they, could their representation of, for example, these cloud-radiative feedbacks or misrepresentation of them lead to some of their struggles in reproducing, TC intensity climatologies, for example. So how do global models compare to these observations? So we've done similar calculations of these radiative feedbacks across 5 different reanalyses data sets, as well as a collection of different climate models. It's a somewhat kind of random collection driven by where there's available data to do this. It includes a couple of simulations from the high-res MIP intercomparison as part of CMIP6, as well as some simulations performed by NOAA's Model Diagnostic Task Force. So the gray shading shows the range of the different reanalyses. The colored lines are individual models, and the CloudSat estimate is in the bold black line with the stars. And this is showing in the top row the different long wave feedbacks, and the bottom the different short wave feedbacks as a function of TC intensity. So this is not intensification rate, but intensity itself, going between 10 and 50 meters per second. The left is the total feedback, the middle is the cloud feedback, and the right is the clear sky feedback. So, we didn't really know what to expect when we did this. We were like, well, are the models even going to be in the same universe as the satellite data? It wasn't necessarily obvious. And so we were actually happy to see that the climate model and reanalysis estimates of the radiative feedbacks are comparable to CloudSat. They're in the same universe, which was exciting. And then if we look at it in more detail though, we see particularly looking at the total and the cloud long wave feedback, most models are seeming to underestimate that at weak intensities. So there are a few exceptions, but looking at this cloud long wave feedback, especially up to, maybe 25 meters per second, which is actually where most of the tropical cyclones lie in these simulations, they're seeing a weaker cloud long wave feedback at a given intensity than the CloudSat observations. And the models also show a stronger intensity dependence of this feedback. So the feedback is increasing with intensity up to sort of hurricane force in the models and reanalyses, whereas in the CloudSat, it's pretty flat with intensity itself. When we look at shortwave, for this wave doing the composite, the shortwave feedback is negative in the CloudSat, but it's positive or close to 0 in most of the models and reanalyses. There's like one. I think this is GL's AM4 model. There's one model that gets a negative shortwave feedback. And then if we look at the clear sky feedbacks, they are quite different. It kind of cancels in the net, but the shortwave is biased low, the long wave is biased high. I would caveat this by recalling that for the CloudSat data, we're actually using water vapor from ECMWF to do the radiative transfer calculation. So it's kind of a misnomer to say that this is an observational estimate of the clear sky feedback. It's an estimate of the clear sky feedback using forecast model data sampled 2 CloudSat overpasses for observed storms versus looking at climate model reanalysis compositing over, whatever their storms that they create are. So I don't really know where this is coming from, but it is quite notable. Nevertheless, it cancels in the net, and so if we look at the total feedback, it pretty much follows along with cloud feedback, essentially. So this is still ongoing work, but at least it's an initial attempt to have the ability to now validate the representation of these processes in models. So to conclude, I've shown here that both idealized cloud-resolving model simulations as well as satellite data agree that radiative feedbacks contribute to tropical cyclone development, and specifically it's the effect of ice clouds on long-wave radiation that's the most important, and the mechanism is that the anomalous warming of the lower to mid-troposphere below those clouds enhances the tropical cyclone's overturning circulation and moistens the troposphere in the inner core. Now, one thing that people often ask me is, well, is it really ice that matters? Is it the fact that it's ice or the fact that the clouds are high? And we actually tested this by going back in the radiative transfer calculations and just swapping what we called liquid and ice, so like forcing it to have liquid clouds, near the tropopause, and you get basically the same thing. So it's the height that matters, not so much the phase difference. And then we've also found, again, both across the models and the observations, that this long-wave cloud feedback is stronger in tropical cyclones that are intensifying more rapidly. And so this suggests that, among the many other processes that contribute to TC intensification, especially rapid intensification, this is one that we should take into account. And thus improving the representation of these feedbacks in forecast models has the potential to yield perhaps advancements in TC prediction. And in fact, a paper by Woodall last year showed that in model forecasts that actually have better representations of these feedbacks compared to satellite data, they actually were more skillful forecasts. So I think that there's a lot of evidence now that this matters, and of course these feedbacks are present in forecast models, but they perhaps could be more attention put to kind of improving, the representation of really the ice cloud amount and distribution would be the main thing that drives this. And then in my group, we have this ongoing work, contributed by my students, Sun Young, as well as Jarrett Starr, to validate the representation of this feedback in models. So thanks very much. I'd be happy to take them.
Questions? I saw Quentin first and then Dave.
Well, yeah, very good talk. Thank you for sharing all this. Really interesting. My question kind of concerns, so, you looked at these idealized simulations, which were, I guess, spontaneous enough, and then a lot of the observational work had been more in the, I guess, when a TC still exists. So I'm curious about your perspective of in the real world. In Genesis, we often have an incipient disturbance that already has a heating profile, already has a cloud distribution, maybe more top heavy or something like that. So I'm curious if you think that in the Genesis process that there could be differences in the contributions of some of these feedbacks when you already have clouds that exist that maybe have different profiles than when you have a TC that is already looking like a TC.
Yeah, it's a good question. So in these simulations, I wouldn't really actually characterize it as spontaneous genesis because they are initialized from this moist bubble. So yeah, there's not a circulation that it's initialized from, but a balanced circulation in response to that moist bubble happens really quickly. I have separate simulations that are truly spontaneous TC genesis, and the results between the two are very consistent in terms of the role of the cloud-radiative feedbacks, suggesting, yeah, in both cases it really is this initial early stage development where they matter the most. And we have also, in an earlier paper in 2020 with James Rupert, looked in case study simulations of Hurricane Maria and Typhoon Haiyan, doing similar sorts of experiments, and we changed the time at which we zero out the clouds to remove the cloud-radiative feedback. And so removing the cloud-radiative feedback before the storm has formed is most effective at slowing down its formation. But even if we removed the feedback after you already had an existing tropical cyclone, in the case of Maria, it still sort of dampened its intensification. It didn't get as strong as if you had that radiative feedback in there. So I think this, combined with other work that have been done by other people, suggests it's really across this hierarchy of simulations that these feedbacks are contributing regardless of whether or not there's an existing circulation. The way I would think of it is that, it's not something that's absolutely necessary, but it helps speed the process up, regardless of whether you're starting from an initial disturbance or nothing. And so we have some ongoing work actually looking at these cloud-radiative feedbacks in tropical disturbances, so things that are not tropical cyclones but could become tropical cyclones, to try to determine, I think, exactly what you're getting at, whether at a given appropriate measure of disturbance intensity, of differences in their radiative heating rate structure and these feedbacks, is that sort of like a predictive factor of whether that disturbance will or will not form into a tropical cyclone. So we don't have an answer to that yet, but we're working on it.
Yeah. Dave, you may need to repeat the question too.
Oh, sorry, yeah.
No, it's okay. I didn't mention it.
Well, this is going to be a really long question. Okay, so I mean, I know some work, and maybe you did too, and I think Brian does, that when you get to high intensity, in short stage, that the long wave feedbacks are negative on intensity. Your primary indicator of intensity and also the forcing is the moist static energy anomaly, right? The moist static energy pleasure. So all your plots basically, so you have a positive feedback going up to the high values, with the high intensities, right? Your curve is still low. But if you look at the actual intensity of the storms, there are papers showing that the long wave feedback basically limits intensity at the high end. So I would comment on that. Like, it seems, at the for high intensity, there seems to be a little bit of a mismatch of continuing to use moist static energy as an indicator of the intensity and the feedbacks, but compared to the actual intensity, which might be going down instead of back up.
Okay, so the question is about how well moist static energy variance really corresponds to TC intensity, and in particular, if we get at higher intensities, do we lose that correspondence? The long wave feedbacks can actually reduce TC intensity at high TC intensities. Yeah, so I am familiar with some of that work. I think, that's why in part we are limiting this to this initial sort of development phase, because I think that's, empirically that's when we see this strong relationship between intensity and the MSE variance. And that's when it seems, also experimentally, that the radiative effects are most effective. I think that after you kind of reach max intensity, there can be other variability in intensity that's unrelated to what's going on with the MSE variance, driven by example, eye replacement cycles, interactions with other sorts of circulation features that are, somehow not affecting moisture distribution. And so I would say that, moist static energy variance is an effective measure of the warming and moistening local warming and moistening that characterizes the initial stage of TC development. It's not a metric of TC intensity. It's probably, I think I recall a paper that showed it actually throughout the full sort of life cycle of the storm, actually better correlated with more integrated metrics of TC intensity, like integrated kinetic energy or things like that. So I don't know the full answer to, what exactly, how you actually connect yet is very, also this maximum it's very, right, it's the maximum intensity at a specific point, like how you connect that dynamic metric to this. It's for me, it's more of a convenience, as then it gives us a way of quantifying this feedback. But even if you remove everything related to the MSC variance, you still have this result that you have stronger radiative heating anomalies that drive stronger circulations of a particular structure to enhance TC development in storms that are intensifying rapidly in their early phases of development. So I think even if you don't trust this as a metric, this is the best metric for this feedback, I think there's still evidence that the feedback is playing a role. I guess I have seen work that shows that when you turn the long-wave feedback off, you can get to storms of higher intensity than otherwise. I guess I don't know. I wouldn't really, at least in my simulations, I don't see that effect. It might depend on the method by which you're turning the radiative feedbacks on and off, because there's different ways that people do that. But my initial thoughts.
So you're saying in these simulations that the actual, what we would call like the standard intensity, the maximum surface wind speed, those are actually
they're very similar. If you compare,
aren't they going down? Some of the black curves going down.
They do. Well, that's why I say I wouldn't really trust it in these simulations. So in simulations like this, where you have a hurricane in a doubly periodic box, it is common to see that you form the hurricane and then it kind of starts to decay. It sort of kills itself, or it takes an incredibly long time to equilibrate in these simulations. But so that's why I said the intensities are similar. I wouldn't necessarily trust what's going on in the ends of these simulations. I think they're better suited to looking at the initial development.
Sure.
So I see, let's see, 3 hands. It's 5 after 12, so don't feel obligated to stay. The 2 Brians and then Sim. Soden, I saw Brian Soden's hand first.
So I was interested in your results showing the importance of feedbacks and the rapid intensification. I was kind of surprised by that just because of the difference in magnitude between latent heating at that stage and then intensity much larger than radiant heating. And I was wondering, is it the feedback itself that's at that stage that's driving or accelerating the rapid intensification, or do you think it's the feedback during the development stage that's setting up a more favorable environment for future rapid intensification? And I was, maybe you've done this, I was wondering what would happen if you, in the control simulation, then you just turn off radiative feedbacks once it reaches a certain intensity when the tropical storm settings. Do you have you thought about that?
So I guess the question is about the causality, I guess, between the strength of the feedback and rapid intensification, for example, is shown here. So I haven't done what you suggest about turning the feedback off at different points along the simulation. That would be an interesting thing to try. I mean, here in this particular plot, this is showing the feedback just before tropical storm force, and then this is showing the intensification rate after that. So this would be saying that kind of having a stronger feedback at a particular instance makes it more likely you would then have stronger intensification subsequent to that. I've done this for all different possible intensity bins, and the results, as long as you're still in the early stages, the results are pretty similar to that. So, I mean, I think this is sort of, leading to that direction of the causality.
Okay, staying with Sam here, good, clean academic fun you can have. Somewhere between sold and unsurprised that switching off radiation entirely, has these important things. Have you tried? I'm curious though, is the top cooling important? Is the top heaviness of the warming important? Have you tried redistributing your radiative tendencies in the vertical? That might be closer to what's really at stake with better and worse models of microphysics and false speeds and overlaps and optics and all the cloudy radiation, as a practice. Switching it off is just, nobody's not used radiation for a long time, real models, right?
Yeah, so the question is about, is it really more about the verticals, structure, redistributing?
Yeah, how much does that matter?
So, well, first I would say that we do not switch radiation off in these simulations.
Yeah, right.
There's always
Right.
radiative heating or cooling.
Yeah.
I'm changing the things that are contributing to that and how much spatial variability that there is. And I do think that distinction is important because, you're testing a completely different thing if you just fully turn radiation off. It also completely messes with your mean state.
Yeah.
So it's not very comparable. I haven't tried redistributing it in the vertical. I mean, one thing that we have done is when we're computing the Sawyer-Leeson calculation for the circulation, that we've sort of limited it to different heights and depths and things like that. Because, in some of the earlier work on this, there was a lot of sort of work suggesting it's really this, cloud top cooling that's enhancing things. And it's really not that. It's the lower to mid tropospheric warming that is most effective, at least at driving this deep overturning circulation that matters.
The opposite, wouldn't it?
Yeah, exactly. I think I didn't mention it here, but we also looked separately at the influences of the amount of ice versus the effective radius of ice, and it's really the amount that matters. So I would say, it's a combination of the amount of ice that you have and how high it is. So having more ice higher is going to give you stronger variability in the rate of heat rates and thus feedback.
If it's just total column heating, then it's just OLR at the top.
Yeah.
Sim?
Yeah, I was wondering, could you use airborne radar data similar to what you're doing with the CloudSat, but that would be in a three-dimensional framework instead of the two-dimensional? And if not, could you, what else would you need in order to do that?
So I guess my question back to you then, because I am not as familiar with this, would be, is that airborne radar data, does that give you good retrievals of cloud condensate? Because that's the thing that you need. If it does, then that would be great. If you want to quantify the feedbacks in terms of this moist-static energy budget, you also need moist-static energy, which you could get from dropsondes. So I have another student who has been working on using dropson data to kind of make a climatology of moist-static energy variability in tropical cyclones and look at how that compares across TCs of different intensity, intensification rate, and so on and so forth. But we haven't had the ability to combine that with either radiation itself or what would be needed for it to actually give feedbacks. But yeah, I think if you could, then that would be super valuable.
Okay, thanks again. And so Allison will be at the wet lab later on today. Also has a empty slot at 2:30. She'll be in the visitor's office if anybody wants to catch up.